Bode diagram is a graphical representation for the frequency response of a system. In Bode diagrams, you have two graphs, one which plots the magnitude response of the system, and the second one which plots the phase response of the system. So you have two separate graphs in Bode diagrams, and this horizontal axis is logarithmic scale. This is not a linear scale, it is a logarithmic scale on the horizontal axis. So what is reason to take this logarithmic scale? Right, right. Generally, you are more interested in the low frequency behavior of the system, at lower frequencies, because almost all real physical systems are low pass filters. So their behavior at low frequencies is more important. And with this logarithmic scale, the this lower frequency behavior, that is magnified. uh, if we use the linear scale over here, uh, on this horizontal axis, you see that frequencies from let's say 0.01 to up to 10, these are covered by this small region, whereas the same frequency region is covered over here by a larger section of this graph. That is the low frequency behavior of the system that is magnified, and we are generally more interested in the low frequency behavior of the systems. And the you can cover wider range of frequencies if you take logarithmic scale. So this we already know, frequency response can be obtained from the transfer function by substituting s equal to j omega, and this becomes a complex number. It has magnitude and phase, and the plot of this thing, phase angle, that is the phase response, and plot of the magnitude, that is the magnitude response. And furthermore, you do not directly plot the magnitude, rather you convert this magnitude in dBs and then plot it. That is, you take the log of the magnitude and multiply it by 20. So what is the reason to plot magnitude in dBs? So again, there are two advantages. Firstly, smaller signals are amply magnified, so we can even see the behavior of signals which are smaller. And second advantage, which we shall see later, is that plotting the Bode diagrams by hand, that becomes much more simplified if you take the magnitude in dBs. You can also utilize MATLAB to obtain the Bode diagrams. You already know how to enter the transfer function of the system into MATLAB, and once you have the transfer function, you can use the command Bode to get the Bode diagram for that particular system. So many times you will not have MATLAB readily available with you, so you should also know how to sketch the Bode diagrams using by hand, how to sketch the Bode diagrams by hand very easily. And furthermore, this will also be important when you will be designing the controllers using frequency domain approaches. You should know how the Bode diagrams of different types of transfer functions looks like. Therefore, we shall learn how to sketch the Bode diagrams of different transfer functions without any software tools. So these Bode diagrams are called asymptotic Bode diagrams, and we take different transfer functions and we shall obtain the Bode diagrams for these transfer functions. The simplest transfer function is given over here. G of s is equal to s, and frequency response can be obtained by substituting s equal to j omega. So this is the frequency response. The magnitude of this complex number, that is simply equal to omega, and the phase angle is 90 degrees. Phase angle of this complex number, this is purely imaginary number, and therefore phase angle of this imaginary number, that is 90 degrees. And we do not directly plot the magnitude, we convert it into dBs, that is, we take the log of magnitude and multiply it by 20. So 20 log of omega, that is magnitude of the magnitude response of the system in dBs. So here is the graph paper. It is not a linear graph paper. You can see that it is semi-log graph paper. On the horizontal axis, these boxes are not equally spaced. This kind of graph paper is called semi-log graph paper. You have logarithmic graph on the horizontal axis, and vertical axis is linear axis. Vertically, all these boxes are equally spaced, and you will have two graphs, one for the phase plot and one for the magnitude plot. You cannot start the frequency on this log scale from 0. You cannot start it from 0. You will have to start it from some non-zero positive number. Let's if we start it from 0.01, what is this next this thing? This will be 0.02, next will be 0.03, and so on, and this will be 1, 0.1, sorry, this is 0.1, and next this will be 0.2, 0.3, and this will be 1, and so on. So frequency from here up to here, you have this is called 1 decade. If you multiply this frequency with 10, you get this frequency. So this frequency range is called 1 decade of frequency. Angles, this angle, let's call it 0 degree. You have plus degree, 90 degree, minus 90 degree, and minus 180 degree. So the what is phase angle of this complex number? Phase angle for all frequencies, that is equal to 90 degrees. So phase plot is very simple. You have a straight line over here. For all frequencies, this phase angle is 90 degrees. And what about the magnitude? Let's take the different frequencies. For example, for frequency equal to 1, omega equal to 1, what is log of 1? Log of 1 is 0, and 20 multiplied by 0 is 0. So magnitude of this complex number in dBs corresponding to this frequency, that is this thing 0 dBs. So this 0 dB for this frequency. And what is magnitude for frequency equal to 10? So log of 10 is 1, and 1 multiplied by 20 is 20. So 20 dBs. So for this frequency, you have the magnitude is 20 dBs, and this graph straight line, that is the magnitude plot, magnitude frequency response of this particular system. You can see that from here to here there is 1 decade of frequency, and there is a rise of 20 dBs in 1 decade. So slope of this line is 20 dBs per decade. So now whenever you will have this transfer function, you will quickly sketch it by a straight line with a slope of 20 dBs per decade, magnitude plot. And for the phase plot, you will have 90 degrees of phase angle. Another transfer function, 1 over s, its frequency response is 1 over j omega by substituting s equal to j omega, which can also be written into this particular format. Bringing j in the numerator, it becomes minus j over omega. And what is the phase angle of magnitude of this complex number is simply 1 over omega, and phase angle is minus 90 degrees. This magnitude written in dBs. So we have take the log of this magnitude and multiply it by 20. And what is log of 1 over omega? That is equal to minus log of omega. So we have minus 20 log of omega. That is the magnitude response, and phase angle for all frequencies, that is always equal to 90 degrees. Again, we have the same graph paper. This phase plot can be easily sketched. For all frequencies, phase angle is minus 90 degrees. that is depicted over here. What about the magnitude plot? What is the difference between this equation and the one which we have seen on the previous slide? We have a similar equation. The only difference is that here is minus 20. So the graph for this magnitude response is a line, straight line, with a slope of minus 20 dBs per decade. And to plot a line, you need information about two things. Firstly, slope of that line and any point on that line. So one point which can be easily determined, that corresponds to frequency equal to 1. For that particular frequency, what is magnitude? Magnitude in dBs, that is equal to 0. So you have information about this point and information about the slope of the line. You can easily draw that particular line. So Bode diagram for this transfer function, again frequency response can be obtained by substituting s equal to j omega. So you have this frequency response, and magnitude of this complex number, what is that? Magnitude of complex number, that is equal to square of the real part plus square of the imaginary part whole square root. So this is magnitude response of this transfer function. And in dBs, we take the log of this number and multiply it by 20 to convert it into dBs. And furthermore, we can take the square root outside of this log. So that is equal to 1 by 2 multiplied by 20 log of this thing inside this square root term. So which becomes 10 log of 1 plus omega square or a square. So all these things are very familiar to all of you. That is why we are going quickly through these things. We take the different frequencies. When frequency omega is very small, so what will be omega over a? Omega over a will be a small number, and its square will be further smaller. So if we want to have a rough sketch of the frequency response, we can ignore this term at lower frequencies. When we have lower frequencies, so we can ignore this thing. So at lower frequencies, magnitude of this thing, that is equal to nearly equal to 0 dBs. And at higher frequencies, what is situation? At higher frequencies, this omega over a will be larger than 1. Its square will be still more larger than 1, and in that case we can ignore this thing. This will be smaller compared to this term, so we can ignore it. So at higher frequencies, this is the situation. 20 log of this thing, 20 log of this thing, that is 10 log of omega square over a square. We have simply ignored this one, and we can even take this square outside of this log. So we get 20 log of omega over a, which is equal to 20 log of omega minus 20 log of a. So this is again the equation of a straight line with the horizontal axis given by log of omega. And what is this? This is intercept of the line on the vertical axis. We can very easily draw the frequency response. Slope of this line 20 dBs per decade. So at low frequencies, what is magnitude? 0. At high frequencies, we have this straight line. So at frequencies up to this a, that is omega less than a, we draw a straight line with equal to 0 dBs. So you draw a line up to this particular frequency with a slope of 0 dBs, and after that you draw a line with a slope of 20 dBs per decade. So this scale is oriented at 20 dBs per decade. From this frequency up to this frequencies, you have 1 decade, and on the vertical axis there is a rise of 20 dBs. So slope of this scale is 20 dBs per decade, and we have to draw this line at this point. Uh, so we bring the scale over here, draw this line. So this is the asymptotic magnitude plot of this transfer function. This particular frequency, this is called corner frequency. This diagram, magnitude diagram, is not accurate diagram. This is called asymptotic diagram. At lower frequencies, it will be fairly accurate. At the higher frequencies, it will be accurate. However, at the frequencies where both of these things are not very accurate, so this graph will not be much accurate. So you can sometimes draw it more accurately by a freehand sketch. So instead of making a corner over here, you draw a freehand sketch to make it a little bit more accurate. So that is the magnitude frequency response of this transfer function. What about phase response? For phase response, again we draw the asymptotic plots. That is phase angle at lower frequencies, that is when omega is much smaller. We can ignore this term, omega over a will be much smaller. And what will be phase angle? You have only one, which is a real number, positive real number, and phase angle of a positive real number, that is equal to 0. So at lower frequencies, phase angle is equal to 0. At higher frequencies, this term is much larger than this term, so you can just ignore this term and you have a purely imaginary number, and phase angle of a purely imaginary number, that is 90 degrees plus 90 degrees. What you do is that you first locate the corner frequency, that is this frequency A. You locate this frequency. You also locate a frequency which is 1 decade higher than this corner frequency. You also locate a frequency which is 1 decade lower than the corner frequency. So up to this frequency, which is 1 decade below the corner frequency, the phase angle of this complex number, that is 0. And at higher frequencies, 1 decade after the corner frequency, you have a phase angle of 90 degrees, and in between you join it by a straight line. So this is asymptotic Bode plot for this particular transfer function. Let's talk about one more transfer function, and then we shall conclude today's lecture, because I am seeing many sleeping faces. So we have this transfer function, and frequency response is given by this expression, simply by substituting s equal to j omega, and the magnitude of this complex number, that is the magnitude of the complex number in the numerator divided by magnitude of the complex number in the denominator. And since we want to plot the magnitude response in dBs, so we shall take the log of this complex number, and we shall log of this magnitude and then multiply it by 20. So that is the magnitude in dBs, which can be written in this form. We can take the inverse of this thing and multiply it by minus 20, that is by the rules of logarithm, which you already know. And we can take this square root outside, so we have minus 10 log of 1 plus omega square over a square. And we can first locate the corner frequency. If the frequency is much smaller than the corner frequency, what is magnitude of this complex number? Magnitude of this complex number is equal to 0, because we can just ignore this term. Omega over a is smaller than 1 and its square is further smaller than 1, so we can just ignore that particular term, and 10 log of 1, that is equal to 0. And at higher frequencies, you have this thing. You can ignore plus 1 from here, and then you get this expression, this square in this these terms can be taken outside. You have minus 20 log of omega over a, which can be written in this particular form. That is, again, you have an equation of a straight line. You already know that equation, y is equal to mx plus c. So this slope is minus 20. This log of omega is on the horizontal axis, and this is the intercept on vertical axis. So here you again locate the corner frequency A, and 1 decade after the corner frequency. So what you do is that up to this corner frequency, you draw a line with 0 dBs. So you draw this line, and after that you draw a line with a slope of minus 20 dBs per decade. So slope of this line is minus 20 dBs per decade. What about the you can also make a correction over here. Instead of making it making a corner over here, you can smoothen this graph by a freehand sketch. And for the frequency, at very low frequencies, phase angle of this complex number, you can just ignore this term. So 1 over 1 is some positive real number, and phase angle of that positive real number, that is 0. At higher frequencies, phase angle becomes minus 90 degrees. So again, to draw the asymptotic Bode diagrams, you can locate the corner frequency 1 decade below the corner frequency and 1 decade after the corner frequency. Up to this particular frequency, you can draw a line with 0 degrees, and from here onwards you draw a line with minus 90 degrees of phase angle, and then join these two lines by a straight line. So this is the asymptotic Bode diagram for this particular transfer function. So the advantage of sketching it by hand is that many times you will not have software tools available to you, and the second advantage is that once you plot these Bode diagrams by hand, you get an idea that what will be the effect of adding poles and zeros to the system, and then therefore we shall manipulate these Bode diagrams to design our controllers. Just like we have manipulated root locus, we already knew that what is the effect of adding poles and zeros to the root locus and how that will be affected by those poles and zeros, and therefore we easily reshaped the root locus. Similarly, over here, once we know what is the effect of adding poles and zeros to this Bode diagram, we shall be able to reshape these Bode diagrams and therefore design controller for systems. So in the next lecture, we shall talk about Bode diagrams for a few more transfer functions a little bit more complex than this one.